I'm here with Professor Steve Furber CBE here at Manchester University. Thanks very much for your time you're giving to us here. Just like to talk to you really about Acorn and your involvement with Acorn and really what it's led to today. You obviously were born and raised here in Manchester and went down to Cambridge to study university there. What got you involved with Acorn?
Well, I was at the university. I read maths as an undergraduate, and I went on to do a PhD in aerodynamics. And during my PhD, I got interested in aspects of flight, and then I heard about the formation of the Cambridge University Processor Group, and I thought, well, maybe I should join up with these guys and see if I can build myself a flight simulator or something like that. So I was involved in the University Processor Group from its foundation, although I wasn't actually a founder. I went along to the very first meetings and started building computers for fun, which was fairly scary in those days because the components had to be ordered by mail order using a credit card from California. And I was a student, so credit cards were fairly scary then, and using them internationally was even more scary. But we got the microprocessors. My first machine was based on the Signetics 2650, which not many people have heard of these days. And it had a full kilobyte of static RAM, main memory, and I assembled printed circuit boards using VeriWire, which was a little wiring pen where you hand wire the things together, and you soldered it, which melted the insulation to make the connections, and I understand it gave off carcinogenic vapours. But it hasn't got me yet. So that's how I built these things, and I built myself a small rack. Couldn't afford a commercial rack, so I made one, and got this 2650 system going. And in the processor group, the enthusiasts exchanged notes with each other, and I remember Sophie Wilson coming around to my house for one meeting of the processor group, looking at my machine and poking away at it and finding faults in the memory and stuff like that. And then while I was still a PhD student in the engineering department, Herman Hauser came knocking on my door. Explained that he and Chris Curry were thinking of starting a consultancy company in the microprocessor business, and they'd been, looking to the University Processor Group as the source of technical people who might be able to help them with this. And he asked me if I was interested. And I said, well, I'm just a hobbyist. I've been doing this for fun, but if you think I can help, I'm willing to give it a go. And that's how I joined the embryonic Acorn before it was Acorn.
Was it based inside Sinclair's building at the time? I believe that sort of started there.
Yeah, the first things we did were in the Science of Cambridge building in King's Parade, where Chris Curry was set up running Science of Cambridge with Clive, and Herman and Chris did bits of Acorn work in there. In fact, the first thing I did for Acorn it was actually not for Acorn, it was for Science of Cambridge. I hand-built the prototype MK14. So I got the circuit diagram and built one using VeriWire and solder in my front room. And the MK14 was basically a copy of a National Semiconductor SCAMP development kit. And they'd taken what was a mass-programmed ROM in the development kit and they'd copied it into two fusible link proms for the MK14, and they managed to copy it wrong. So I debugged this thing in my front room. That was the first piece of work I did for them.
Fantastic.
And then Chris and Herman got a contract to do some development work on microprocessor controlled fruit machines, which were very new at that time. Up to that date, fruit machines had all been controlled by relays and so on. So this was an early attempt to do microprocessor stuff, and we used two SCAMPs in a rack to control this fruit machine. In fact, the software for that was bootstrapped off the 2650 machine I built in the processor group. It was used as a dumb terminal into the SCAMP development kit, and we brought this fruit machine controller up.
Fantastic.
The the main challenge in those days was to make these things robust.
Yeah.
Because very early on, people had discovered that with electronic cigarette lighters, if you just sparked them next to the fruit machine, they'd often pay out.
Jumps off somewhere else and all sorts of things.
So that was when Sophie Wilson came in. She designed an FM receiver front end, which would trigger whenever you flicked one of these cigarette lighters and cause the scamps to reset. So it would definitely not pay out.
Yeah, fantastic.
That was the requirement. That
Okay.
if you interfered with it should definitely not pay out.
Yeah.
And the things were tested by plugging a mains adapter into the wall, plugging the fruit machine into one socket, and an arc welding transformer into the other.
Yeah, and they just plug it in.
Somebody welded metal together while you operated the fruit machine to see if the thing was prone to.
Right.
That's right. Yeah.
Fantastic. I mean, the whole feeling at that time, it was very much a sort of a hobbyist and people doing processor-based work, just pretty much out of love at that time, wasn't it? You just enjoyed doing that kind of thing.
Yeah.
And the whole industry pretty much come out of that. Is that fair
That's
to
right,
say?
because we are talking the late 1970s now, so we're before the IBM PC. This started before the Apple II had appeared, so there were some very basic box machines. The Altair, I think, probably had appeared about this time in the States.
I was going to say very much a US machine.
Yeah. So in the University Processor Group, the real men built computers out of TTL.
Right.
It was only the wimps like me that used these newfangled microprocessors, which were kind of cheating because you got too much in one package.
Right.
But yes, microprocessors were just entering the public consciousness. So the MK14 from Science of Cambridge was an example of a microprocessor on a printed circuit board with a hexadecimal keypad, a 7-segment
incredibly
display,
rudimentary. Yeah.
and you could put assembly code into it and make it run. And Sophie saw the MK14 and said something which she said many times, which was basically, I could do better than that. Went home with Easter holiday and came back with a design she called the Hawk, which was 6502 based.
Yeah.
And Herman looked at this and thought he could sell it, and that became the Acorn System 1.
Right.
And the name Acorn was introduced originally just as a trading name. The company was called Cambridge Processor Unit Limited.
Yeah. I mean, an interesting point there is that you look at those machines today, the System 1 and the Mark 14, and they are, to what most people would describe as unusable. But these things sold in a big way, really.
Oh, the System 1, yeah, and the MK14 sold faster than people could put kits together.
Yeah.
The System 1, I think, was mainly sold as a kit, so
Yeah.
you got the parts and you had to solder it together.
Mm-hmm.
But yeah, there was lots of interest,
Yeah.
and it was really the only way a member of the general public could get their hands on anything that looked like a computer.
Yeah,
at that
could
time.
actually touch a computer.
Real computers cost £1 million and lived in clean rooms and were only touched by men in white coats. Whereas
Absolutely.
these things you could buy for $100 or $2 and play with at home.
Yeah, and it was just the want to own one of these things, the want to be able to control one of these things, and a lot of it was driven by the science fiction of it all, and make these things do.
Well, of course, one of the real science fiction aspects is they got used as props in TV shows as well.
Yeah.
So the Acorn System 1 was featured as the computer on Blake 7.
Yeah.
There was quite a lot of competition between Acorn and Sinclair at the time, and Clive Sinclair had proudly boasted that you could control the nuclear power station with the ZX81.
Yeah.
Well, this was nothing compared with controlling a 21st century
Absolutely.
interstellar cargo ship with an Acorn System 1. So
Win hands down.
that's right.
Fantastic. So, sort of going on a step. I mean, there's a whole lot of history that I know that we're skipping, but to go forward onto the BBC Micro. Obviously, the BBC come to you, or come to Acorn, with this sort of specification for a machine. There was sort of competition with sort of various other manufacturers out there, but long story short, you got it. How did that change things at Acorn from making, I mean, obviously the Atom was out and it was selling well.
Yeah.
But then all of a sudden you were just sort of shot into fame, as it were, I suppose, within the computing industry. to have this machine that was so successful?
Well, I mean, the BBC Micro was a huge phenomenon. Of course, when the BBC came, their spec was a Z80 machine running CPM.
Mm-hmm.
And the BBC Micro was neither Z80 nor CPM, although a little bit later you could buy a Z80 second processor that ran CPM. So we kind of met the spec in the end. But no, they were sufficiently convinced by what we could do with the 6502 that they moved the spec basically to the machine that Acorn had already begun to get on the drawing boards. Everybody knows it was called the Proton,
right?
which was always designed as a dual processor.
Mm-hmm.
So the fact the BBC Micro had second processor connections was actually because the BBC Micro was just the front end of something that was designed as a dual processor from the outset. The BBC Micro was a huge phenomenon. I remember that when the BBC were talking to Acorn, I wasn't involved in the commercial discussions. I was just, I was a techie. That they were confident that this machine would sell on the back of their program. You'd sell 12,000 of these machines. And that was big numbers to Acorn. Not huge numbers. We'd probably sold several thousand atoms, but it was really worth going for. But nobody imagined that would be out by a factor of 100. The 1.5 million were shipped in the end, because nobody really anticipated the wave of interest.
No.
The first thing I really realised that this was a phenomenon was when Sophie, Chris Turner and I agreed to do a seminar at the IET in Savoy Place in London. I don't know if you know the IET. It's got a big central lecture theatre that seats about 500 or 600 people. And they asked us to do a seminar on the BBC Micro. So we set this up, went down there thinking this is a big room, I wonder if they'll fill it. And 3 times the number of people they could get in the room turned up.
Fantastic.
People had booked coaches from Birmingham and they had to be sent home because health and safety said they couldn't let them in. So, nobody was expecting this either.
And when was this?
This would have been 1982, I would guess. Well, now hang on, the machine was first sold in January 82. So it may have been later in 82.
And that was the first time that you really thought, this is big.
This is when you first felt the scale of public interest. People were prepared to hire a coach from Birmingham to go and hear this bunch of techies who probably didn't know how to speak in public anyway say something about this this hobbyist computer thing, which of course we always had the education market in mind for it, but this was much bigger than just the education market in terms of interest. And we actually went on tour with this seminar. We did go and give it twice more at the IET to soak up demand, and they managed applications, so they tried to avoid having people turn up and get them who had to be turned away, because that's clearly not good.
No.
But we did a tour of the UK and Ireland. I remember doing it in the TV studios in Dublin, and everywhere we went there was a big turnout. There was real interest.
What sort of people were they that were coming to this? Just
a wide range of people.
Not just the education background.
I think it's the same phenomenon as with the System 1, but on a bigger scale. It was a bunch of people who recognised that computers were about to become within their reach when they'd been behind closed doors throughout the past history. Now they were about to come in their reach. And there were a lot of companies building machines at the time. I mean, we've mentioned Sinclair, but if you go and look at the machines coming out, the 80s was a real era of diversity. Wonderful, quirky machines of all shapes and flavours, all coming out of companies a bit like Acorn, small startups, enthusiasts, that the public couldn't perhaps fully trust. Unless you were a hobbyist and real enthusiast yourself, you didn't know who to trust. And then the BBC put their name on this machine from Acorn, and you knew, one name you can trust is the BBC. And I think that really was the key to the success of the BBC Micro. There was a huge wave of interest, and the BBC backing for it meant you could trust it.
Seal the deal.
And so it really rose, even though, by the standards of the competition, it was a slightly expensive machine. I was going
to ask about that.
It was slightly high spec, right? And that was partly the BBC's requirements. I mean, the BBC imposed. Well, no, imposed is the wrong word, but encouraged us to go for a particular spec. The spec was all negotiated and agreed. There was no imposition. But they were tough negotiations. The BBC had a pretty clear idea of what they wanted, and all of these things, and the fact that we pushed the technology a bit. We ran the memory a bit faster. We made an early use of semi-custom chips. So we had these 2 Ferranti ULAs that gave us quite a lot of excitement. All pushed the price of the machine up a bit. So it was an expensive machine, but despite that, a much broader market was comfortable with it because it had the BBC's name on it.
Yeah, absolutely. I mean, you had a very, very expandable machine as well. I mean, it's always been recognised as a machine that you can pretty much connect to anything.
Oh yeah.
And the amount of peripherals and things that then come out afterwards.
And of course, the machine itself was low level. So if you connected something to the back like a joystick, it was easy to communicate with it because you weren't, as you would be with today's PC, you're so high up in the software stack that seeing your bespoke bit of hardware that you've poked in the bottom is something that very few people can do. Whereas with the BBC Micro, it was easy. Right? Anybody could read the user guide, and if they had a little bit of technical nous, they could build their own electronics to go into the 1 megahertz bus and program it. It was easy. And I'm quite sad we've lost some of that, actually. I think it's much tougher now for teenagers with a bit of technical interest to say, I want to build one of these things, plug it into my computer and make it do stuff. The really bright ones can do that.
It was a question that was for later about that, actually. But might as well go on to it. I mean, that's exactly my feeling, is that I had the opportunity, I did have a BBC Micro as it happened, to connect up various different bits of equipment to it, and to program this thing down to the metal. You are talking to the chips, you're talking to those very pins that you've just wired up something to. And like you say, that's completely gone. You've gone through several layers. You have to talk through Windows to this, that, or whatever. For somebody that wants to get into it now, how do they do it? Because I bought a BBC, and it wasn't long before I had the lid off, as with most users, and you could start to get in there and mess with things. You can't do that with hardly any technology now. We're running so fast that you can't even make circuit boards to connect to it because the frequency. It just won't have it. So where do you start now, do you think? Well, just to get into this.
Yeah, so you're right that the problem isn't simply the stacks of software. The problem is that the hardware is now... The signal level hardware is very difficult to work with and requires a lot of skill and knowledge. But of course you could still build a slow interface. If you want to interface at a megahertz, right, then connecting to a megahertz is no harder now than it was in 1980. I suppose, and actually, a megahertz means you can do 1 million things a second, which is quite a lot for many purposes.
Absolutely.
So how would people access that? Well, I guess they get some of it through the Lego robotic systems and so on. But in a sense, a bit too much of that is prefabricated. It's a bit too ready to go. But you are talking at quite a low level to the microcontroller.
Yeah, that's true.
There's no reason now why we can't make BBC-like products using microcontroller technology. In fact, you could probably make a BBC Micro in a single chip.
There are various projects out there that are trying that at the moment, actually.
And sell it very cheaply. Okay. I can still run BBC Micro programs on my laptop.
Yeah, oh, absolutely.
In fact, I have BBC Basic for Windows, which is a very faithful emulation. In fact, it's produced by Richard Russell, who was one of the people who worked for the BBC when we were negotiating with them in the 1980s.
Oh, right.
But what I normally do is I actually have an Archimedes emulator, which I run on the PC, and I have a BBC emulator that I run on the Archimedes emulator that runs on the PC. And there are
Emulating emulation.
and it's still faster than the original BBC Micro because that's how much compute power we've got now.
Absolutely.
So you can still run the stuff, but you can't interface hardware to it so easily.
I found quite a number of people come to us, probably sort of my sort of age 40s, and they might know kids and things that are just into messing around with it, but they go back to that old technology and they say, get an old BBC off of eBay, and we'll wire things up to it, and that,
Do they?
yeah, absolutely, and and I do it, and it's something that is still, it's very accessible, and the machines are sort of plentiful, and they're sort of coming around again, really, as a sort of training aid.
Yeah, and you're not the first person I've heard from that there's an interest in actually building something much more basic again. That around today's microcontroller technology, where you've got a keyboard and a whole lot of pins you can connect things to.
PIC processors and things like that.
And my guess is the market for that is small but not insignificant.
It's just for those who you can see they've got an inclination to go into this sort of industry, to play a part in it, and I feel it's quite difficult for them to have anything hands-on from an early age,
Yeah. I think the nearest thing you'll get at the moment is if you go into Maplins, you can buy a PIC development kit for about 20 quid. And with the PC, if you've got a PC already, you can write PIC assembly code, load it into the PIC, and do all sorts of stuff with it. And I do know quite a few people who use PICs this way.
Yeah, so I was hugely following for PIC processors.
Yeah, so that's probably the nearest you get. Yeah. But with the PIC, in some sense, you're going to a lower level interface than on a BBC Micro. You've got to be more technical and be prepared to go deeper into the technology to use a PIC. So something that was just a bit higher level.
Yeah.
Obviously, you probably want to base it on an ARM microcontroller, wouldn't you?
Absolutely, you would. Yeah, absolutely, you would. We'll come on to that later. So, I mean, just to go back to a point then about the price of the BBC, I mean, it was expensive. There's no two ways about it. I mean, you had sort of Spectrums and that kind of thing come around, which were under half the price. Was that a big part of the negotiations? Was trying to keep the price down, or was it? It was.
Well, I mean, you may remember that in fact that we launched. I may get the numbers wrong here, but we launched the Model A at 239 or something.
Yeah, something like that. Yeah.
And the B at 339.
Yeah.
But really, we couldn't make them
it
at
was
that
later.
price. So
not very long before they went up.
They went up to 299, 399.
Yeah.
But yeah, so we were trying hard to keep the price down. But really, you couldn't. How could you make the machine cheaper?
No.
If you look at a machine like a Spectrum, then of course everything about it is cheaper, including the keyboard.
Yeah.
The BBC had actually, by today's standard, a stunningly high quality keyboard. Today's keyboards are very cheap, elastomeric. Every switch on the BBC Micro keyboard had a pair of gold wires that touched when they crossed. And then when you pushed the key down, they sprang together and touched. Yeah. So you weren't making the contact by the key press, you were removing the obstruction that was preventing the contact.
Right.
And BBC keyboards were formidably robust.
Yeah.
There were some manufacturing problems with them. There was a batch that were manufactured with the key switches about 0.5 millimetre off the PCB. Right. Which meant when you hammered on them, the force got transmitted through to the solder joints on the back, and then the PCB tracks broke. But when they were made properly, they would last 10 years of kids thrashing them.
Absolutely.
But the machine took a hammering. Mine still works.
Yeah, as does many of ours actually. Yeah, they're fantastic machines. So I mean, with the success of the BBC Micro in the sort of general arena of computing, what did that do to Acorn?
Well, Acorn grew rapidly. So when the BBC contract was signed, I was still actually a research fellow at the university. My day job was doing aerodynamics, and I guess Acorn at that stage employed maybe 30 people. By 1983. I joined them full time in October '81. By 1983, the company had grown to 400 people, just to manage this stuff. And of course, there was no real sales activity involved because the stuff sold faster than you could make it. It just walked off the shelves. Right. So it was really building the technical team up. And of course, we had a strong manufacturing team. If you're going to make millions, you've got to know something about procurement. And, and Acorn didn't actually manufacture, it was all subcontracted, but you had to manage the subcontractors. So we had to build skills in manufacture. But the BBC contract also required lots of exotic technology beyond the basic machine. So, you know, the Prestel telesoftware receiver was a bit of unknown technology we had to make. The second processors, including the Z80 running CPM. So there were lots of things to go around it. So we grew technical teams. We also realised that the price point was actually quite good for schools and professional users. But it was too high for hobbyists and most home users. So we developed the Electron, which was a cost-reduced BBC Micro. Not an entirely happy story, but not much wrong with the machine. But you know, for Christmas '83, when there would have been a huge market, we couldn't get the electronics reliable enough. And by '84, when we cracked it, and we could make lots of them, the market had gone. So we ended up with 250,000 of them in a warehouse that were eventually sold below cost price. So we tried to cost engineer it down, unsuccessfully as it happens. But yeah, the company went from, you know, a small startup, experimental startup, to a big established, well, 400 big, medium size maybe.
Time in computing, I mean, and it was there sort of a feeling that you know, you guys ruled the world when it comes to computing? What was the atmosphere with the people that worked there? Well, or was it lost in the number of people?
No, there was a core group who did the really ambitious technical stuff, and we did begin to get the idea that we could, you know, take on anything. Right? We knew there was competition. We were a bit over-focused on Sinclair as the competition. Standard problem, seeing the parochial competition and missing the real competition from much further away. But technically we felt very much on top of what we were trying to do, and we kept taking on bigger and bigger challenges technically, and it kept working and selling. So we kind of felt we developed the Midas touch when it came to advanced technology, and of course that's a lot of the background to the development of the ARM microprocessor. This is a very short period of time when you look back. You know, the first sale of the BBC Micro was January '81. The ARM design started in earnest October '83, so 2.5 years later, and the first ARM chips were in our hands in April '85. So we're still only sort of 4 years from beginning to sell BBC Micros to having ARM chips in our hands.
So going on to the ARM chip then, how did that come about? What sort of started you guys working on a new type of processor? Well,
the Advanced R&D group, which I was in with Sophie and several other folk, we were responsible for sort of looking furthest out in terms of what the company was going to do for products. I mean, Herman was very hands-on. He was always very involved in this. So we were already thinking, well, the BBC Micro has been a big success. We need to build on this. What do we do for a follow-on machine? We can put second processors on, which kind of tied us over for a bit. But really we need to be thinking about the next big machine. And it was clear that we were going to step up from 8 bits. 16-bit processors were already around and going into some competing products. So we looked at the 16-bit processors that were around at the time, and we didn't like them. We built machines. We built bench prototypes of machines with these, and we didn't like them for 2 reasons. Firstly, they were all going to 16 bits by adopting mini computer-style instruction sets, which meant they had some very complex instructions. The anecdote I always remember is that the National Semiconductor 32016 had a memory-to-memory divide instruction, which took 360 clock cycles to complete.
Really?
right? And it was running at 6 megahertz, so 360 clock cycles was 60 microseconds. It was not interruptible while that instruction was executing, and single density floppies, if you handle them cheaply with interrupts, give you an interrupt every 64 microseconds, double density every 32. Hence, you couldn't handle double density floppy disks, which everybody, even the Beeb, had gone double density by this point, and you couldn't handle those with a 3216 without spending money on hardware. So, the complex instruction sets gave them very poor real-time response. That's the best way to summarise it. And the second problem we had was that none of them kept up with memory. So commodity memory at the time was, as it still is today, DRAM. It was rather smaller DRAM chips. And this DRAM had a certain bandwidth. If you ran the DRAM at full spec, you get a certain bandwidth. And we'd deduced from a number of experiments that compute power goes with memory bandwidth. But these microprocessors wouldn't even use the bandwidth that was there. They couldn't keep up with the memory. And this struck us as the wrong answer. So we were sitting there feeling unsatisfied with microprocessors we could go out and buy. And I'm pretty sure it was Herman dropped a couple of papers on our desks, which were early RISC papers from Berkeley and Stanford, where a grad school had designed a microprocessor that was competitive with the best industry could offer, and they'd done it in a year. And we looked at this and we thought, well, how would we really like a microprocessor to look? And Sophie began tinkering with instruction set architecture, inspired considerably by the Berkeley and Stanford RISC work, but also by what she understood of the 6502, and also what was needed to write a good basic interpreter. Sophie had written several basic interpreters by then, for the Atom, for the BBC Micro, for the 3216 second processor, and so on. And she sketched out an instruction set. And then in October 1983, there was a sort of formative visit where Sophie and I went to visit the Western Design Center in Phoenix, Arizona, where they were designing a slightly extended 6502. The 24-bit address 6502 that became, I think, it's 65C816, if I remember my part numbers. And we went there expecting to find, big, shiny American office buildings with lots of glass windows and fancy coffee machines. And what we found was they were working out of a bungalow in the suburbs of Phoenix. They hired, school kids during the summer vac to do some of the basic cell design. Yeah, they got some big equipment, but they were basically doing this on Apple IIs. And my strong memory is we walked out of there saying to each other, well, if they can design a microprocessor, so can we. Right. So we went back, talked a bit more to Herman, and from the tinkering which Sophie had been doing with instruction set design, which Herman had entirely supported and approved of, we put the project on an official footing and said, we're going to set about seeing if we can design a microprocessor. The other, if you like, infrastructure aspect of this is that Andy Hopper from Cambridge Computer Lab, who was a director at Acorn, had persuaded Herman that if he was serious about staying in the computer business, he needed to get serious about chip design. So Andy had advised Herman to get chip design tools from VLSI Technology and Apollo workstations, and they'd recruited, I think, 3 IC designers, a group led by Robert Heaton. I can't remember precisely the order they came in, but Jamie Urquhart came early, Dave Howard, Harry Oldham, all names still associated with ARM.
Absolutely.
And so we got these tools and the IC designers, but no chips for them to design, right? So this was so strategic it had been paid and bought in without actually having anything for it to do. And Sophie and I were thinking, well, maybe we should have a go at designing our own microprocessor. We looked at this RISC stuff and we thought, well, this is kind of obvious. Right? This is a good idea. So we'll set off using these ideas and try and put something together. But it's clear that big industry's got far more resource. They're going to pick up on these ideas too because they work. So we're just going to get squashed, run underfoot by big industry as it catches up. But if we set about doing this, we'll learn something. We'll understand something about what it takes to build a good microprocessor, and then we'll be better at recognising a good one when we see it.
All right. Okay.
Right? So you see, we didn't expect this to go through. And to us, building microprocessors was a black art. The big companies had hundreds of people, and it took them 10 revs of the chip before it started to work sensibly. Yeah. It just looked like a black hole, and Acorn couldn't afford that size of black hole. Right. So we set on it, and it turned out there is no magic. Microprocessor is just a lump of logic like everything else we've designed. Absolutely. There are no formidable hurdles. The RISC idea was a good one. It made things much simpler. And 18 months later, after about 10 or 12 man years of work, we had a working ARM in our hands.
Fantastic.
Which probably surprised us as much as it surprised everybody else. Although I do remember in July of '85, we had the processor on our bench running for a couple of months. We decided it's time to say something to the public about this. Yeah. So I rang up a journalist that I had contact with, and I said, we'd like to sort of put something out. We've been working on this microprocessor design, and we've now got it working. And he said, I don't believe you.
Really?
If you'd been doing this, I'd have known. And put the phone down. So we'd actually done this in considerable secrecy.
Yeah, absolutely.
And the secrecy was so good that we could even persuade people when we got the working silicon in our hands that we'd done this. That was and in terms of timescale, of course, this was all happening exactly at the time when Acorn was going bust and being rescued by Olivetti.
Yeah.
And I believe Olivetti wasn't told about the ARM when they bought Acorn. So when they bought it, we thought, well, maybe it's time to own up. And they didn't know what to do with it.
Right. Fantastic. And so we're talking about a chip now that is in something like 92 or something % of mobile devices, phones and things like that today? Is that right?
Yeah, at the end of 2007, the 10,000 millionth ARM had been shipped. Right, so there are more ARMs than people on the planet. I believe production is currently running at about 10 million a day, but it's projected to rise to about 1 per person on the planet per year within 2 or 3 years. So,
they're mind-blowing numbers. I mean, again, did you ever consider
no.
it? No. What does it feel like to know that you played
it's kind of magic, isn't it? I mean, it's largely serendipity.
But
I spent my last 2 years at Acorn, or some of my last 2 years, trying to work out how to build a business plan for a company that could take ARM out. It was clear Acorn's desktop PC business was not big enough to support proper processor development. We needed a bigger market. So I tried to work out how to spin out a company, and I could never get the numbers to work. You had to sell millions of these things before the royalties started paying the bills. Well, the way I say that is intended to convey that we couldn't imagine selling millions of these things.
No, absolutely.
Let alone billions, which is where we are now. But a lot has happened to take that. It hasn't gone there all on its own. So when the company was spun out, Robin Saxby was brought in, and he and the team evolved this business model, which has been instrumental in its success. I mean, had it not, had Apple not come knocking at the door, wanting the ARM for the Newton, and Robin Saxby being brought in to head it up, there are lots of ifs.
Of course, yeah.
If these things hadn't happened,
we
wouldn't be where we are today. But where we are today, I've been trying to work this out. I suspect there's more ARM computing power on the planet than everything else ever made put together.
It's phenomenal, isn't it?
The numbers are just astronomical.
And it's, from my point of view, it's looking at all this and seeing how it's changed us as people. To have this computing power in our pockets, it's just completely changed sort of the way we are and the way we live our lives.
Yeah.
And you've played an absolute key part in that.
Well, we kicked some stuff off, but it's huge numbers of people.
Oh, of course, yeah.
You can say, well, if Apple hadn't come knocking, if ARM hadn't formed, then the ARM processor would have disappeared. Nobody would have heard of it. I don't think the products in your pocket would be that different.
Possibly
right?
not.
I think
but
the ARM model has facilitated standardisation across mobile phones. It's probably moved it forward a bit quicker than it would have happened without the ARM. But you'd have a mobile phone powered by a development of the Motorola 68K or maybe the MIPS processor, or there'd be something else in there doing pretty much the same. But ARM was the right product at the right time.
Yeah.
It was just perfect at the time the company was formed for the emerging system-on-chip business. In the early 90s, you could just think about taking the 4 chips that you needed to build the Archimedes system and putting them onto one chip, right? And the fact that the ARM was the smallest processor around just meant there was more silicon real estate for everything else.
Yeah.
So at that time, small really mattered.
It's low power as well, isn't it? I mean, that's one of the key aspects of it.
Well, the low power is one of the great accidents of history, isn't it? I mean, it's not an accident now, but we designed the ARM for an Acorn desktop product, a tethered product, where power is not of primary importance, but it had to be cheap. So cheap meant it had to go in a plastic package. Plastic packages have a fairly high thermal resistance, so we had to bring it in under a watt.
Right.
Okay.
Right.
So power was an issue. The tools we had for estimating its power were not at all reliable.
Right.
And so we used Victorian engineering. We made sure it was going to come in under a watt, and it came in under 1/10 of a watt. Right. It's an anecdote. When we had the first ARMs in the test cards, I wanted to measure the power. Okay, and the way you measure the power is you isolate all the power pins, and then you reconnect them with an ammeter. It's not very difficult. So I set this up and started it running, and there it was computing. And I hadn't connected the power pin. Right. So there's this ARM running in a board with none of its supply pins connected, and it was still computing. Right. It was running the code, talking to the host. And of course, what was happening was that provided some of the inputs or output, no, it have to be an input. So provided some of the inputs were a logic 1, the electrostatic protection diodes would feed that in, and that would bring the power rail up, and that would get the CMOS logic. And because it was so low power, you could power it through a protection diode. So the thing would work with no power at all, apparently.
Magic.
Yeah, so that's one of the things I remember. But yeah, so it came in low power, and yes, early system on chip, low power was important, but I think small size was more important.
Right. Yeah.
The first ARM used 25,000 transistors, which was less than a Z80.
Right.
So it was a really small, simple piece of design. And in the early 90s, when ARM Limited was formed, that really mattered. Modern ARMs, if you look at the Cortex A8 in the Apple 3GS iPhone, right? It's a dual issue something or other. I've no idea how many. I bet it's vast numbers of transistors compared with an earlier ARM. Pipelines much deeper to get the performance up and so on. These days, the silicon real estate is enormous compared with early 90s, but back then in the early 90s, keeping the processor small meant you could do system integration to a bigger degree, and that mattered.
Well, that's fantastic. So, leading on from ARM processors, I believe you're working on a project at the minute called SpiNNaker project? Brainbox?
Well, yeah, we call it SpiNNaker. The University Marketing Department has decided to call it Brainbox, which was interesting when they put out the first press release, because it was almost good in terms of marketing, because it got lots of pickup for that name. But of course, it also got on Slashdot. It got picked up by Slashdot, and 150 quotes down this, I was responsible for the end of humanity. Right. It was very interesting to read this progression of comments getting increasingly idiotic. It was perfectly clear that nobody had got past the word Brainbox. If you look at my website,
read the story in detail.
You'll find there's quite a lot of detail on the website. We've published 10 peer-reviewed papers you can read and find out some truth. But of course, that's too much work if you're going to type something into Slashdot.
Absolutely. Yeah.
So it's, and have been trying to be careful to avoid that kind of conclusion. You know,
Right.
we're building
Yeah.
a machine that's going to emulate the brain, and you know that.
But it's just repeating itself, though, isn't it? I mean, because going back to early computing, I mean, the various sort of programs were out there that they were put out to try and you know, take the fear away from people, because these home computers were starting to be so prevalent,
Yeah.
and they were starting to be used in industry, and we're going to lose our jobs, and they're going to take over this, and you know, and it just didn't happen. It just sort of moved those jobs to other areas. But it's kind of just happening again, really, isn't it? And it's just the fear of the unknown, I think.
Yes, so it's an understandable fear, but you know, if you look at the facts, with a SpiNNaker machine where we're planning to put 1 million ARM processors to work in a single machine, that'll get us to about 1% of the human brain. Okay, if we built a machine 100 times that big, it would, you know, cost the order of £100 million. It would consume the order of 5 megawatts of electricity. Right?
Yeah.
There are much cheaper ways to make brains than that. Okay?
Right.
You know, biology is quite good at making human brains. They're cheap, they're incredibly low power, about 20 watts. And they fit inside your head, right? And they're quite convenient to carry around. You know, the machine that could do that, I mean, it's going to be jolly inconvenient. So why do we do it? Well, the answer is that there are quite fundamental scientific questions to be answered about how the brain works.
Yeah.
If we can answer those, it may give us strong hints as to how we can improve treatment for various forms of mental illness.
Yeah.
We may find ways to raise the level at which we can interact with computers, so that, you know, my experience of computers is that whenever you get a new one, you have to do a lot of learning to learn how to use it.
Yeah.
Mobile phone. It still takes you, you know, most people never bother. But if you really want to master a mobile phone, you've got to spend days poking away at it.
Yeah, those features.
And I'd like to reverse that.
Right.
You know, I think when you get a new computer, it should spend days learning how to be used by you.
Right.
And you should simply, you know, give it instructions and tell it when it's wrong. And I think that does require us to understand more of how we work, if we want to make machines that try and meet us halfway.
Yeah.
But a lot of this work is motivated by the pure science. I mean, wouldn't it actually be quite interesting to know how our brains work?
Well, absolutely.
I mean, wouldn't that give us some fundamental insights into the kind of animals we are? And isn't science worth some level of investment in its own right? You know, despite, you know, ignoring all the potential benefits that so often emerge from this, simply acquiring the knowledge seems to me to be worthwhile.
Yeah, definitely. And that is, like you said, building a machine based around ARM processors. There's 1 million of them, you say?
The ultimate machine will have 1 million ARM processors. We're putting about 20 on a chip.
Right.
So 1 million is 50,000 chips, right? It's not going to fit in your pocket anytime soon.
Yeah.
And yes, and this is based on fairly simple models of neurons, which are the technology inside the brain.
Yeah.
Okay, we can't build high accuracy neuron models at the level of efficiency required to get to 1% of the brain with 1 million ARM cores. You need a lot more processors than that to do that. But my assumption is that a lot of what's interesting about what's happening in the brain is to do with network level interactions, and we can model that with relatively simplified models of the neurons. And so with 1 million arms, we expect to be able to model about 1,000 neurons per arm, and so that's about 1 billion neurons, which is about 1%. So that's the goal. Of course, we aren't going to build a machine that's suddenly going to tell us how the brain works. Okay, we're going to build a machine that will allow neuroscientists to test hypotheses, allow psychologists to test hypotheses. So we're in Manchester, we're working with our psychology colleagues who have a neural network model they use for learning about reading disorders. In children there are reading disorders such as dyslexia, but in adults there are reading disorders that are a result of injuries such as strokes.
Right. Yeah.
And they have networks they can train up, which basically learn to read. They do text to speech, and they train these up, and then they break bits of them, and by selecting which bits they break, they can emulate most pathologies, and then use these models to develop treatments before they try them on patients. So they effectively have a computer that is the guinea pig for the therapy.
Yeah, right.
And if it works on the computer, you then move it to the patient.
Right.
So,
Incredible.
but at the moment, they're limited as to the scale of network they can
Yeah.
train by the computing resource, and we plan to use the SpiNNaker machine to execute their models to allow them to scale up to richer models of how people learn to read.
Right.
And there's a clear hope that will lead to better clinical treatments.
Yeah.
And that's a model that we would hope to repeat. So if we're looking at results from neuroscience rather than psychology, we'd again be looking to work with neuroscientists who would propose models of how networks interconnect, and then we'd be able to map them onto the computer, run them in real time, because we're aiming for a real-time model,
Right.
and give the results back and say, do these look like what you see in the lab or not? So the machine isn't magically going to solve this problem on its own. It's a platform for research in this area.
Yeah. You should allow other departments then to try out those ideas that they've had nothing to do on before. So
that's
fantastic.
Right. Yeah.
Right. So, at the risk of this answer being involving SpiNNaker projects and ARM devices, where do you see the future of computing going?
Generically, that's quite a hard question.
Absolutely.
And computing is now very broad.
Mm-hmm.
Okay, so, and there's important computing right across the spectrum. So at one end there are the data centers.
Mm-hmm.
Okay, everybody's used to using Google. I don't suppose many people know how Google works.
Where that information's coming from? No, absolutely.
And the fact that Google has warehouses full of computers that service those queries.
Mm-hmm.
And Google's average electricity consumption is now about 1 gigawatt.
Mm-hmm.
Okay,
Yeah.
so they spend $1 billion a year on electricity bills, and
Incredible.
That's characteristic. The power consumption of data centers is becoming a great concern.
Yeah.
I think we'll see great progress in getting the power of data centers down.
Mm-hmm.
Okay, so
we need to.
so high-end computing has tended to largely ignore power so far, but it's about to start learning.
Yeah.
Now, of course, there's good places to learn from, because at the other end of the spectrum, the mobile consumer electronics has become phenomenally good at eking CPU cycles out of small batteries.
Yeah.
And if we could transfer some of that technology into data centers, we could save huge amounts of electricity.
Yeah.
At the consumer end, I don't think I've got any more of an insight into where it's going than anybody else. I mean, you can see the trends. The products, such as the iPhone 3GS, deliver a phenomenal amount of computing power into an environment where a lot of the machine cycles go into a user interface. Mm-hmm. The iPhone may be the best exemplar of what I described earlier, of the machine coming closer to you, doing things intuitively.
Right.
That's going to continue. We can continue to make the machines more powerful and more energy efficient, at least for another decade or so. Things get pretty tough in chip technology about 10 years out. The atomic scales are really beginning to hurt. In terms of how transistors behave. Mm-hmm. And there's research on how we cope with that, but I can't see my way through that at the moment, any more than anybody else can. Digital media is kind of coming together. So what you see is electronics conquering. First music went digital, then photography went digital. Now we're in the middle of movies going digital.
Absolutely.
And that's sort of it for the media we know how to handle. I mean, there isn't. That's everything basically.
Yeah.
I mean, we haven't worked out how to do efficient electronic smells yet, but that's maybe a good thing. And electronic touch is fairly primitive. But for the basic passive media stuff you sit and listen to or watch, once we've conquered movies, videos, TV, then I think it's difficult to see where we go next.
No, absolutely.
And the video is almost done.
Yeah.
So you know,
I mean, the whole convergence thing with having all of this just on one device that you carry around with you now, you know, it's here now.
And in the home, you see, you know, I've still got a computer and a TV, and I've got a hard disk, you know, personal video recorder box, and I've got this stack of CDs in the corner of the room and a CD player. Well, I think all that can now go away. You can now get the single box with the hard disk in, the Blu-ray disc drive, connects to the TV. You can dump all your photos onto it, all your CDs onto it, and it all sits in one place. And it's effectively the computer-based jukebox that just does everything you need in that corner of the home and tidies things up nicely. And that's just arriving now, particularly if you insist it should be high definition, because I think it'll only converge at high definition. For a lot of TV, the difference between standard definition and high definition is not really worth that much. No, there are some programs.
People just can't see it.
Some programs look great in HD. The big nature programs, the big scene programs, but standard TV drama, I don't think really gets anything from going HD.
No, if it's a good story, it's a good story. It doesn't really matter.
That's right.
Yeah.
In fact, there were good stories in black and white.
Absolutely. Yeah.
So whether it's worth actually allocating that much digital space to store everything in HD, I'm not sure. But I think once we've got to HD, I can't really see you need to double the resolution again. I don't think you'll see anything. No. So that the issue with convergence in the home, I think, is that it's just a bit too expensive at the moment. If you want to converge on a Blu-ray hard disk.
Are you somebody that wants to?
Sorry?
Are you somebody that wants to? Or
yeah, I'd like to save some space. You know, put the CDs in a box in the garage for backup. Okay. Yeah. The original CD now becomes the backup medium, and everything's just.
So it's not the vinyl then that's sitting in the corner.
The vinyl's already sitting in the garage.
So it's, you know, one of the types that likes the vinyl for the sound and the...
I still have a turntable capable of playing vinyl. It so rarely gets used that every time I get it out, I have to replace the rubber belt because it's polished again, and it's getting increasingly difficult. I'm from the area where everybody at university either had a Garrard SP25 Mark III auto changer, or if they were a bit more purist like me, they had a Goldring G101 belt-driven transcription turntable. And mine's the Goldring, and getting spare rubber belts for them is
not easy.
Still possible, but not easy.
Yeah, absolutely.
So
I went the direct drive route, didn't have that problem.
Well, sometime soon I think I'm probably going to have to invest in a USB drive. Turntable. Move everything across and then get rid of them. And I don't know how long the CDs will stay after that.
Well, I mean, there's been problems with that already, hasn't there? I mean, with CDs sort of delaminating and the interaction between the metal film inside and the adhesives that they used. I think there's certain Dire Straits albums that when you bought in the first place, they were DDD, so they're completely digital, and now they're just sort of bronze-coloured sort of coasters.
They're now coasters. I don't know. I've not had trouble with the CD yet, and I've had CDs since the early 80s, I think. So some of mine are that old, and you know, the first time I really realised that CDs were a good thing was when I came downstairs and found my young daughter spreading marmalade on the CDs. She got them. She was 2, and she got them out, and she was.
She must watch Tomorrow's World then.
And
that's what they told you could do.
Right, and you know, I took them, ran them under the tap, cleaned them all off, and they've worked fine ever since.
Absolutely.
Which wouldn't have been the case with the vinyl, I don't think.
No.
Anyway, that's.
I mean, the whole thing with digital data and people assuming that it's basically bomb-proof. You know, once you've got it, but it's not always the case, is it? I mean, we suffer at the museum with bit rot on EPROMs and all sorts of things. You know, CDs have failed and everything. So just this complete reliance on
that's why you need
digital technology.
That's why you need to get it into one place on a hard drive that you can back up.
Yeah, absolutely. The backup's the key.
Right. Yeah. So you've got to have multiple copies, and then I think you're reasonably safe, as long as you don't keep all the copies in the same place.
Yeah, well, this is where the web comes in again, isn't it? And being able to back up to somewhere on the web that's somewhere else. So, well, thank you very much for your time. It's been really interesting. Well, what can I say? Thank you for the BBC.
Okay.
Thank you very much.
Okay, you're welcome, and good luck with the museum.